Okay, good. Welcome to the class. Sorry for a bit of a delay. We'll blame it on Google Cloud Sync and things like that. We had some trouble with syncing the slides. I want to make two quick announcements. First is that we have in the schedule for the class, we have 1 week we had 1 week of gap that we could use in a good way. And we thought that we will use this 1 week gap in a good way to give you a 1 week extension on homework 2. Okay, so rather than making the homework due this Thursday, we are making it due, or actually we are making it due a week later. Together with that, we are also releasing updated version or more user-friendly version of the code for question 2.4. Okay, so two announcements are: we give you more time for homework 2, and we are releasing updated version of code. All this is also written on Piazza. We decided to do that because I think it will all help you, and it will also help us make your experience better. So that's announcement. So what are we doing today? Today we are going to talk about generative models, but we will use some of the technology we have talked about so far. In particular, what we talked about so far is to take the graph, take the nodes, little local networks, and think of this as neural networks to be able to make predictions about the nodes at the end, right? So the recap was that we are taking the graph, we are unrolling the graph structure around that node to create now the neural network structure. We then talked about how in these boxes we have these trainable operators that allow us to learn how to aggregate and propagate information over these graphs. And then what was a new concept that is fundamentally different than how we usually think of neural networks is that every node in this case has a different neural network structure, because the structure of the neural network itself depends on the structure of the network around the given node. And there is beautiful theory that tells you how do you design these aggregation operators so that this neural network, when you pass information through, remembers both what are the properties of the nodes, their features, but also what is the structure of the network itself, right? So if you want to say, I want to be able to distinguish this node and that node, and if you don't get any information from the features from the node, then when you are aggregating, you should remember that there are 3 nodes here while there are 4 here. And at this level, we should remember or be able to capture that here we are aggregating from 1 node, and here we are aggregating from 2 nodes, for example. So there are ways to do that, and the ways we have talked about this in the class allow us that this network, as the information is propagated, both learns to aggregate the feature information as well as capture the structure of this neural network. So it basically, and if the embedding captures the structure of this network, this means that the embedding captures the structure of the network around the node in the graph itself. Okay, so that's the important thing. So again, what is different from traditional neural networks is that we are doing 2 things at the same time. We want to learn from the feature information, but we want this neural network to also learn or capture its own structure, because that means that this node will know how the structure of the neural network around it looks like. That's what I will say here. Right, and we talked about 2 methods that are able to do this. We talked about the graph convolutional neural networks, or GCN, that basically say, let's take the messages from the neighbors and let's average them together. And then we talked about GraphSage, which is a generalization of this that allows you to not aggregate from all the nodes, allows you to aggregate from subsets of the nodes, and allows you to aggregate in this generalized way, which gives you much better performance in practice. So that's a review of what we talked a week ago. So as I showed you this picture, we talked about how do you go from the graph to some vector embedding of the nodes. What we want to do today is we want to go the other way. We want to generate graphs. So what it means is we will want to start with something here, and we want to kind of travel in this direction so that out comes the graph. Okay, that's what we'd like to do conceptually, right? So before we were saying, how do we encode graph information? into some vector. Now we will say how I decode from this vector the entire graph structure. That's what we do. So we go the other way. So the outline for the lecture today will be that I'll first introduce the problem of graph generation. I'll tell you some basics of fundamentals of machine learning for graph generation. We'll talk about this model called graph RNN, and then we'll talk about applications and open questions, and I'll probably end here, and that will be fine. Okay? So graph generation, right? We talked about this a bit before, right? In terms of null models and trying to capture properties of networks that we see in real life. Remember, clustering coefficients and things like that we talked about. What I want to do today is to say, given a graph, I want to generate a synthetic version. The question is, what is a good model? And then the question is, how do I feed the model to generate the graph? The uses of this are numerous, right? You can use this to generate interesting new structures and to gain insight into how real graphs could be generated. It allows you to do anomaly detection, because you can say, is the real graph similar to what the synthetic graphs are, or the other way around? Allows you to maybe use this for predictions and predicting future graph structures. Graph generation is useful because it allows you to then to use these graphs for simulation of different algorithms. Graph generation is very useful because you can many times describe problems as graphs. So for example, our group, we have a paper how you can generate satisfiability instances using graph generation. You could imagine that you could use graph generation to generate synthetic images where you want to describe the relationships between objects in the image, and based on that description, you generate the graph. So first you generate the image. So first you want to generate the graph of what is where and how it's related, and then you can use that to generate image. So there is a lot of places where, as a step of a generative process, you may want to first generate the skeleton, kind of the relationship structure, and then generate the real thing, right? Graph completion is another example, and I'll show you more, right? So one application that I'll show you about is generating novel molecules, right? If you want to develop a new drug, drug is a molecule. Molecule is a graph. So if you want to generate novel molecules, or molecules that have high values of certain properties, these methods are what we learn about today allows you to do that. So I'll talk about two things. I'll talk about realistic graph generation. So we'll get to this from kind of purely machine learning point of view, where we say all we care about is a black box that generates a good graph. And we kind of don't care about the black box so much, which is very different than what we talked about the small world model and so on, which were these kind of very mechanistic graph generation models that were much more, where the goal was much more to see whether that graph generation process looks realistic. And then in terms of applications, as I mentioned, you can push this a step further, and you can talk about goal-directed graph generation, where you can say, can I generate graphs that optimize given objectives? And if you generate drugs, you say, can I generate a molecule that optimizes treatment, or that is non-toxic, or that it's soluble, and so on. So these are the applications of this technology. So as I said, we want to have a box that generates realistic graphs. If we want to generate molecules, we'd like our graphs to look like molecules, like I show you in this slide. What we can also do is to say, can I do graph completion, where the idea would be that you have part of the molecule already generated, and you want to complete that molecule to the end. Why would you maybe want to do this? Is to say, oh, I have some active part of the molecule that I know has therapeutic effect, but I want this to be this molecule to be stable. So I want to print the rest of it so that the molecule will be maybe more soluble, right? So this is not soluble. I print the rest of it. Now is much more soluble, right? Those are the ideas. And just to show you how well our models will work, our models will be able to generate, the same model will be able to generate very different graph structures. We'll be able to generate grids. We'll be able to generate this type of community structures. And we'll also be able to generate this kind of scale-free power law graph structures that look much more tree-like. And the point is that the same model will be able to do that, right? And what is also cool, like generating a grid is actually quite exciting because it's this, you have to be able to learn this like super regular pattern, right? While these other patterns are kind of more stochastic. So it's very impressive that the same model can do something so regular as this, as well as something much more kind of stochastic looking as these two other graphs. So that's what we are going to do today, okay? Now, why is this hard, right? If you say, I want to generate a graph, then what you really need to do is you need to generate an adjacency matrix, right? And we already talked about Kronecker graph generation, if you guys remember, when we were doing this recursive matrix generation, right? The issue is that a graph on n nodes, the output space is of order n squared, right? I need to, for every node, I need to specify all other nodes it connects to and all other nodes it does not connect to. So if I want to have n nodes, I need to generate n square bits of information, right? The other thing is that if I would generate this as a fixed size matrix, I have the problem that graph sizes differ, right? Like molecules have different sizes. So it's not clear how could I generate different graphs of different sizes. And then just kind of what I try to illustrate here is that the n squared is a lot, right? If you want to have 1,000 nodes, then n squared is 1,000,000, right? So these things get big very, very quickly. Okay? And then there is another issue, and this is this issue of uniqueness, right? The issue is that if I have a graph and I order the nodes in some way, here is the graph adjacency matrix. And right, like I have node 1 that links to nodes 2 and 3. So node 1 links to nodes 2 and 3. But here, right, somehow I renumbered the nodes. This is now node 1, node 2, 3, 4, and 5. So now node 1 links to nodes 4 and 5. So node 1 links to 4 and 5, right? So what's the point? The point is that I have the same graph, but I have two wildly different representations of it, two very different adjacency matrices, right? So it's not clear what do I do, because this ordering of the nodes is totally arbitrary. I can number them this way, I can number them some other way. But the output I would get is very different, even though in some sense it should be the same. It's the same graph, right? So we have this huge problem of non-uniqueness, that a graph on n nodes can be represented in n factorial ways, right? And n factorial is really, really, really a lot, right? So this is why this is hard. And another reason why this is hard is that you need to have long-range dependencies, right? If I would like to generate a graph on a cycle on 6 nodes, then if, let's say, I generate it step by step, then, you know, I would start here, and then here I say, oh, link back, link back, link back, link back. But here I say, aha, you must not link to this guy. You have to link back so that when the next guy comes, I say, aha, link here and link there. So I need to be able to somehow count, you know, I need my network to be able to count up to 6 and then decide, oh, now I need to not just link back, but I also need to link forward. And if you think about when I was showing you the ways we generate the grid, we need to be able to count how many steps did we do so that we can then do the next one, right? And here we need to be able to count up to 6. So it means we have a dependency that is 6 steps deep, if you think of it this way, right? I need to carry 6 steps of information or history that I know that when this guy comes, I also have to connect them here, right? So that's a lot of information or a lot of memory that I need to carry to know when to connect to the first guy and when to just keep connecting to the last one, right? So just think about that, right? Generating a cycle is actually non-trivial because you need to remember when to finish the cycle. Okay, so this was about the problem and why is it hard. So let me now tell you some fundamentals of graph generation. Okay, so what are we trying to do? How are we thinking about this? So the way we think about this, we will we will think that we are given a set of graphs, right? And this set of graphs is coming to us from some data distribution, right? So if I have a set of molecules, then the data distribution is the distribution of molecules that appear in the real world, and I'm getting some samples, some subset of those I get to see, right? And my goal would be, right, that I'd like to capture this distribution of graphs that I see. So I would like to use this probability distribution that is generating me the data, and I would like to mimic it using my model, right? So that once I have this probability distribution mimicked by the model, I'm able to learn the distribution, and I need to be able to draw samples from it, right? Which in our case will be quite complicated, because we are not sampling a uniform random number on 0, 1. We are sampling an entire graph. So I need to be able to sample from this distribution of graphs that I learned over, right? So this is very hard. In some sense, these concepts are simple, but the complexity of the objects over which we are playing is very hard, right? So to recap, I'm given a set of graphs. I would like to learn, right? I assume that these graphs are coming from some generative process, from some data distribution. Nature is a good generative process, right? And I would like to learn a model that captures this distribution, but not only capture it, but also allow us to generate new samples, new instances from that distribution. Yes, go ahead.
Does this data require many different variants of the same type of graph?
No, right? The point is, whatever is this, it is. Right, so this could be molecules, it could be molecules plus social networks, whatever is the data generation process. I kind of don't care, it's given to me, right? And I know this is what we'd like to capture. Now, if these are molecules, you would imagine, this is a, nice tight distribution. But if you'd be a chemist, you'd say, how can this be tight? I know these are these types of molecules and that types of molecules. So, this distribution is very complex. So we don't make any assumption about the homogeneity. Like, just think of this as the meta level for now. Yes?
Is the goal to have P model as close to P data as possible, or are you trying to make some variant of it?
Good question. So the question is the goal of this P model to be close to P data? Exactly. That will be exactly the goal, and we'll talk about it. All right. Good. So here is the setup. The setup is that assume we want to learn a generative model from a set of data points. In our case, or a set of observations. And in our case, observations are entire graphs. Okay. And we will have this P data, which will be the data distribution, which is never known to us, right? This is, kind of what God has in his head, right? Or whoever, like nature has it in its head, if you want to think of it that way, right? And all we see is what the nature reveals to us, right? Some real molecules, real social networks, whatever we get to see here, right? And our goal will be to come up with this approximation, this P model, that will be parameterized by some parameters. And this P model, we want to use it to approximate this P data, right? So again, with this, nature God type of analogy, I never know what nature thinks. So I'm just trying to approximate what the nature thinks, right? Or whoever generated you the data thinks. You have a question? No? All right, sorry. Okay, good. So what's the goal? The goal is, as you were asking, the goal is to make P model as close to P data as possible. And there is an additional requirement, is not only that we need to be able to match or kind of fit this distribution, we need to be able to sample from it. We need to be able to draw new instances from that distribution, which in our case means we need to generate examples, which means we need to be able to generate graphs from this distribution, right? So we have kind of two requirements. So now let's formalize what does it mean to make P model close to P data. And this means we need to, like we talked about this, but now you will be kind of surprised we arrived to the same concept we already talked about. Is the key principle is this maximum likelihood, right? It's the saying, let's build a model that maximizes the likelihood of my data, right? So we are saying, what is this trying to say? It says, let's go over all possible settings of my model parameters, and let's set these model parameters in such a way that if I take some instances x from my p-data distribution, the probability that these instances are generated by my model is as high as possible, right? Notice here I'm taking expectation, which simply means take a sum, and I have a sum of logarithms. So this is just what is called the log likelihood. And if you go now back to the lecture on community detection and big clam and AGM, this affiliation graph model, there we wrote out the same equation, right? We say, I want a model that is most likely to have generated my data. And if my model optimizes the probability of generating the data I observe, this means my model approximates this data generation distribution, right? So here I'm basically writing out what log likelihood is, and why is this interesting? Because I say data comes from p data. You wanna set parameters of p model so that this sum of probabilities is as large as possible, right? So that's kind of why this makes sense, and how can you understand this, in some sense amazingly fundamental, and also in some sense simple, crisp, pure concept of log likelihood or maximum likelihood. Sorry, question? No? All right. So, right, so our goal is to find parameters, we'll call them theta star, such that the observed data points that come from the p-data distribution, the sum of their log probabilities has the highest possible value among all possible choices of my parameters. And this is what is called maximum likelihood. Now, what does this mean, right? This means let's find the model that is most likely to have generated observed data. The issue here is that we don't know what, let's say, the form of this p data is. So this model is just an approximation to this, right? And here we are making this big assumption that is always hidden in all of machine learning, if you like, that whatever this model is, it will be able to approximate this thing, right? And this is kind of it's a Hail Mary. You just hope it will work, right? Because you can never look into what is really this. Maybe if you are working in, I don't know, chemistry, physics, or in some cases where you actually know, you have kind of scientific insights into the data distribution and the fundamental laws, you can model this kind of more faithfully. In our case, we'll model things with neural networks and we'll say, this is what it is. We just want to approximate it. Yes?
Will we examine the optimization of the thetas? So choose a sort of optimize which model?
Excuse me?
Will we examine optimization of which thetas we use?
Yeah.
So, right, sort of next step optimization.
Mm-hmm. Well, there was no question. I heard.
Will we examine that?
We will talk about it. Yes. Yes.
I think this model here assumes that choosing an x each time is independent.
Exactly.
Is that a valid assumption in practice?
So exactly, great point. So what this is assuming, it's assuming data is IID, which means independent and identically distributed. And what does independent means? That these are independent samples, and identically distributed means they are all samples from this thing, right? And that's the assumption we will make, right? But again, this is a fundamental assumption that most often people don't even think about. They just say, oh, here's the likelihood, yoo-hoo-hoo, let's go, right? So that's a great point, all right? Good. So this is about how to feed the model, how to learn parameters. What we want to do now is we want to be able to sample from this method, from the distribution. We need to generate a graph, right? And our graph is sampled from this very complex distribution. So what will we do is the following. We will say, how about a common approach to generate complex samples is the following, is to say, let's sample a number on a uniformly at random number on an interval 0, 1, right? And then let's have this complex function f that will take this random seed and generate a complex object out of it, right? This is our decoder. If you think of the picture I had, you know, my slide number 5 or whatever, right? I will put a random number here. I will kind of push it through the entire neural network, and out comes my generated graph. Conceptually, you can think of it as that, right? So the idea is I generate some, you know, something from a very simple, let's call it noise distribution. I have a complex function. It takes this noise and gives me this complex object that follows some more complex distribution. And our goal will be that we will use deep neural networks to find this function f. Okay? That's conceptually what we are trying to do. And our example will be a case of what is called autoregressive generative models, right? And let me explain what do I mean by autoregressive, right? Autoregressive means that we will do this generation sequentially, and that the future or the next steps will depend on what we have done so far. So it's a regression, but it's a regression on ourselves, right? So auto means yourself, so it's autoregression. I do it on whatever I have already done. So I'm like fitting a line to whatever I have already generated, right? So we will do this in the following way, right? Why do we want to do this in an autoregressive way is because of the chain rule, right? So if I can take my complex object and separate it out in a kind of into a sequence or a set of some operations, then without loss of generality, I can take my complex distribution over this complex object, and I can write it out as this set of conditionals, right? Where I say, the action at time t depends on everything I have done so far, right? So, you know, first is probability of first action times the probability of the first times the probability of second action given the first one, and then given the first 2, the first 3, the first 4, and so on and so forth, right? So essentially what I'm saying is every next action depends on all the previous ones, okay? Right? So for example, the way you could think about is if x would be a vector, then I could say, you know, xt is the tth dimension of that vector. Or you could say, how do I generate? So how do I generate the vector? Is first I generate the first component. Based on what the first component is, I generate the second one. Based on what the first two are, I generated the third one, and so on. Or if you say I want to generate natural language, I want to generate a sentence, then you could say I generate a sentence as a sequence of words, where the next word depends on all the previous words, right? And again, this can be as complex as possible. You can always factorize it in this type of way using the chain rule, okay? So what will be in our case? In our case, we'll be generating the graph sequentially. So in our case, xt will be the action at time t, which will be add a node, add an edge, right? That's what we will be kind of printing out, okay? So what did we learn? We learned that we want to have this p model, we want it to fit p data, and that we won't directly work with this p model, but we will apply the chain rule to work it, to kind of have these temporal dependencies, and we will rather learn this type of a thing, okay? That's the idea. So what this means is we'll generate our graph sequentially, okay? And this is a graph RNN that I'll talk about now. RNN means for a recurrent neural network, where what does recurrent means is that whatever you output, you feed back in as an input to the next step. And this is exactly what we mean by autoregressive, because basically whatever we have generated so far, the next step will be dependent on everything that we generated so far. Yes?
Is one of the valid actions also like a stop token that says, I'm done, I've made my graph?
Great. Is there a, yes, there are two special tokens. One is SOS and one is SOE. SOS means start of sequence, and SOE will, or EOS will be end of sequence. But yeah, you need those tokens as well. Yes?
the function f that takes in like the noisy sample and then transforms that into x?
Great. What is the conceptually the purpose of function f is that you don't know how to generate the complex thing. So the idea is that you will generate kind of something simple, and then that complex thing will use that as a seed and generate the big thing. Right? That's what f will be doing. And in our case, our f will, it will start with one node and one edge, and it will then kind of bloom and grow into the entire graph. Right? So in our case, f will be this thing that will say, what do I do next? All right? Good. Great. Let me continue. So here is how we will do this. We will do this that we will say, if I have a graph, and let's say the nodes are numbered in some way, I would like to write out what is the generative process, I will call it S, for this graph. And to generate that graph, I start with node 1, then node 2 comes and it connects to node 1, then node 3 comes, it connects to node 1, then node 4 comes, I have to connect it to 2 and 3, and then 5 comes, connect it to 3 and 4, and I'm done. Okay, so that's the recipe to draw a graph. So we'd like to learn this sequential recipe. So the first thing that is important is to realize that, as I said before, graphs can have arbitrary ordering. So I will use the word pi, or the symbol pi, to describe, to say there is some random ordering, this ordering is pi. Okay, so I'm just saying that, in order to generate a graph with a certain ordering or numbering of the nodes pi, then this is uniquely defined by this sequence S. It's indexed by pi because pi determines the numbering of the nodes. And then here is the way this generation process looks like. Note that if I would renumber the nodes differently, then the sequence would be different as well. Right? If this would be node number 2, then my sequence would be add one node, add another node, now add, I don't know, node number 3 that links to 1 and this number 2, and so on. So the sequence would be different. But if you fix the ordering, then the sequence is unique. Right? Because you process these nodes in that given order. And every node only links to all the previous nodes. Right? So you need to fix the ordering, and that's why we use this pi there to say the ordering is fixed. It's given, it can be random, we don't care, but it's there. Yes?
Does this generation process assume that the output graph is fully connected, or is that just like this particular example?
This particular example is not a fully connected graph.
Sorry, you can reach that there's like a path from any other.
So that the graph is connected.
Graph is connected. Sorry.
Okay, great. It does not have to be connected. It does not have to be connected. If you believe that your graph has multiple connected components, you could try your network to learn that. Or you could say, first you would generate the number of connected components, and then you would create each connected component separately. So that's your choice. Yes?
Are we able to add multiple edges in one step? Or are we adding one given edge in one node per step?
We are adding, so for example, here notice we need to add 2 edges per step. Right? So we will be adding multiple edges per step. I will explain. I know there's a lot of questions because it just I haven't explained it yet, but it's a good point. We need to fix this, yes. Okay? So the point is exactly what you asked, is that you need to be able to do 2 things. You need to be able to add nodes, and then you need to be able to add edges. So what this means is that we need 2 generative processes. One generative process is very simple. It just adds one node at a time. Okay? So all it says, so the node level generative process says add node, add node, add node, add node. Okay? And then the interesting one is really this edge generative process that says, now that we have added the node, let's decide where this node will connect. Right? So we will have another generative process that will now say, take the node, don't connect it to node 1, don't connect it to node 2, but connect it to node 3. Okay? So the point is that we need two generative processes. One operates at the node level, right? I label it node 1, node 2, node 3. And then I need another one at the edge level that says edge to previous node number 1, edge to previous node number 2, edge to previous node number 3, right? So what this means, kind of the summary, is that the way we will generate the graph, a given graph with a given node ordering, is that we will model this as a sequence of sequences, right? We will have a sequence of nodes additions, and for every node addition, we will have a sequence of edges that this node creates, right? So the way you can think of it is that we will be kind of printing out this adjacency matrix this way, right? We add the first node, and then we add the second one will add to the first one. Then we'll add the third node needs to either connect to the first one or to the second one. Then we'll add the third node, we need to decide, does it link to the first node, second node, or the third node? And then we'll add, I don't know, the fifth node, and again, we need to decide which of the previous nodes does it connect to. So the way we will be, essentially what we will be printing is we'll be printing this yellow part of the adjacency matrix. That's what we need to learn. We need to learn to generate this sequence, okay? So now, this should be much more clearer, okay? Yes, go ahead.
I don't understand why it is necessary to pick a node ordering before a sequence. Is it okay to generate a sequence and say the first node added is node 1, second node added is node 2, and then permute the ordering later?
If you would permute the node, like, I can show you later, right? If you permute, then if you put this down, like, I don't think that's a, you cannot permute. Like, if you write it out, you cannot permute. It has to be fixed. And if it's fixed, then it's easy to generate. And I will actually show you that picking the good node ordering is very important and allows you to learn much faster. By picking the right node ordering, you can make your graph generation process much easier. So it's important to pick the ordering ahead of time, right? Because again, we don't care in what order we generate. We just care that we generate this type of structure. And I don't care whether you start generating it here or here or here, you choose, right? But if you write the graph from the proper way, it's easier to write it out one way than the other way, right? So that's the idea. Yes?
Can this process be used for generating directed graphs? Like, because we are only considering like half of the adjacency matrix. So
great. So the question is, how would you create directed graphs? What you could always do is that when you generate an edge, you could decide, you could be generating kind of these things across the diagonal at the same time, which would mean you would generate an edge, decide the direction. And then you would allow yourself, whenever, you could even say, I generate an edge, and now I decide, is it one way, the other way, or both ways? So you could do it kind of as another level. So now description of the edge also has the direction information, and you have 3 directions. One way, like up, down, and both ways. All right, good point? Good? Okay. So what have we done so far? We transformed the graph generation problem into a sequence generation problem, and we said we need to model 2 processes. One is the node level, which basically, given what we have generated so far, generates the new node. And then now, given the new node, we need to generate edges for this new node, right? And we will use a recurrent neural network to model these processes, okay? So we will have a node level and an edge level RNN. And the idea will be, right, that the node level RNN will generate the initial state of the edge level RNN, and edge level RNN will use this initial state to generate a sequence of edges. And then after it is done, we will take the state of the node level, edge level RNN and fit it back to the node level RNN to generate the new edge. So that the new node, which then generates the new edge. So basically the idea will be that we will always keep the state as we are moving forward, and this state will keep the memory of what we have generated so far, right? So here is now this tried to be written out, right? So there is the node level, and then top to bottom is edge level, right? And this shows how the state is being kept, right? So what this means is SOS is start of sequence, this is how we initialize the node level RNN. The node level RNN will generate a node, and then its state will be passed to the edge level RNN that will generate the edge. Here is trivial. And now this new state is pushed back to the node level RNN that will generate a new node, pass its state down as initialization to the edge level RNN. Edge level RNN will generate the first edge, generate the second edge, and now it will take its state and put it back to the node level RNN. Node level RNN will do one step, generate one node, take its new hidden state, put it here to the edge level. Again, edge level does the edge, updates the hidden state, does the edge, updates the hidden state, does the edge. Now it takes its own hidden state, pushes it up to the node level RNN, and again, node level adds one node, updates the hidden state, pushes it down back to the edge. Edge is generating edges, taking the hidden state up there, and so on. Okay, so that's the way things will flow. So what we have to do is talk about how to generate the sequence of with RNN and discuss what is a recurrent neural network. And a single cell or a single step of recurrent neural network is the following thing, right? I have the state. This is what we call a hidden state. We have the input and we have the output. And we have a set of parameter matrices. And essentially, the way we think of this is that state comes in here, input comes in here, out goes the output, and the state gets passed forward or updated, right? So the RNN works the following way. We say, given the previous state and the input, I compute the new state, and based on the new state, I make some output. Okay? So that's what is happening, right? I have my state, some nudge comes from the outside, this updates my states, and I scream or whatever, right? So I create some action, right? So that's the idea. And in our case, right, we will take these recurrent neural network cells and we will chain them together, right? So this is now to ask, how will I generate sequences? The way we generate sequences is that the output, y, becomes the input to the next instantiation of the cell, right? So I'll take this and kind of rewire it in here, right? And then here is where the state I will keep track of. So the way you can think of this is the following. I have the recurrent neural network. I will first kick it with start of sequence symbol. It will I will also use the starting state to be start of sequence. I will generate some output. I will update the state. Now I take this output, rewire it in here, put it in again. This thing will say, take the state, the output, generate the new output. I will again update the state so that then I take this new output plus the state to again keep doing this. And at the last step, what I'd like to do is, when I think I'm done, I would like to generate this end of sequence token, which says, we are done with generation. Thank you very much. Here's the graph. Okay? So that is the idea. And because we have this start of sequence, it's clear when we start. And because we have an end of sequence, we know when to stop. So this will roll until one RNN cell will say, hey guys, I have enough. It's end of sequence. Okay? That's the idea. So let's now talk a bit more about this. While this looks great, what is problematic is that if you think of this as graph generation process, and given that there is no randomness in this process so far, right? Like everything here is deterministic. I start with a start sequence, I generate the output, take this output, take it as an input. I never said flip a coin, add some randomness. So this would just learn to generate the same graph over and over and over and over again. So I want to add some randomness, some stochasticity to the model. Right now this is all deterministic, right? You could just write out these two equations and it's all deterministic. So the way we make this stochastic is the following, is to say, rather than to think the output y here is a 0, 1, basically edge, no edge. Now let's think of this as a probability. Okay? And if this is a probability, right, like I write it out there, then now I flip a coin based on this probability to decide whether I get an edge or not. And after I have an edge or not, I put this in as a input to the next cell, right? And now my model is stochastic, because I have a probability, I sample an x, and then I feed the x in. Okay? So there'll be some stochasticity. So what this means is that at each step, the RNN will output some probability vector or some probability. We will then sample from that probability, and then we will feed the sample into the next step, right? And this is how we will get randomness. Okay? So just to say again, what did we change now? Rather than this being, is there edge or no edge, so 0, 1, this is now a probability. We flip a coin. If the coin says edge, then there will be an input here, edge. If the coin says no edge, the input here will be no edge. Okay? That's the idea. So good. So now let's suppose we have already trained the model. So how will this be in our case? This is just a concrete example of what I was saying on the previous slide, right? We initialize everything with start of sequence, and we start, right? We say, aha, here is the first edge, probability, flip a coin. Okay, we decide to put that edge in. Now we take this and feed it in here. That's the next edge, 0.4, flip a coin. Maybe the coin says, yes, let's add an edge again. I feed this in, right? So essentially what we have done is we said we are outputting edge probabilities. There is this stochastic random sampling based on the probability of edge. Whatever the coin says, that's the input to the next cell of the recurrent neural network. Why this is good is because this means that the graphs we will generate, everyone will be a bit different because these coin flips will come out differently, right? So we'll be able to have some variance in the graphs we generated. So this is what happens kind of at the test time, right? And we keep running this until one of these cells says end of sequence, right? And if the network doesn't say end of sequence, we would generate an infinitely large graph. Yes?
This is the edge level RNN?
Yes, you can think of this as an edge level RNN. Exactly. Node level is easier. Yes?
Is the EOS signal deterministic based on
good point. So the point is exactly for the edge level RNN, you don't need an end of sequence because you know how many steps you need to go. But for the edge level RNN, you need to say stop. So that's a good point. All right. So now I want to say, how are we going to train the model? Right? I now showed you how to generate. The question is, how do you train? And the way we will think of the training is, again, we have the y star to be the real sequence of edges, right? So what we will be applying is this notion of teacher forcing, okay? And what is teacher forcing? I feel a bit strange talking about teacher forcing, but what is teacher forcing, right? So teacher forcing is that you replace the output and the input with a real sequence. So essentially, what does this mean is that you initialize your sequence, you start, you get the probability, but you don't flip the coin. You just take the real thing and take that real thing as the input to the next step. And you push it out, you get the probability, but again, you take the real edge and feed that in to the next step. So essentially, you ignore the student and what the student does, but just push the truth to the next step. So essentially what this means is that the teacher is correcting the student after every step. Yes?
How do you enforce the order of
sequence? I thought it's order invariant, right?
How do you increase the order of sequence? Order is given.
How do you order the sequence? Because it's
Order is given, right? The ordering of the nodes is given. We said, right? The ordering of the nodes is given. You get to choose it.
But this is the edge level RNN, not the node level.
But once you have the ordering of the nodes fixed, it means it's clear if you fix the order of nodes, it means you fix the rows and columns of the adjacency matrix. So everything is fixed. Once the order is given, the nodes have unique numbers and everything is fixed.
Does that mean that each graph of size n gives us n factorial training samples?
You could do that if you would like.
Same question.
Yeah. So in principle, you could generate all possible orderings and say, I want to generate one of those. We generally don't do that because there are good orderings and there are hard orderings, right? Because you can think, for example, even generating a cycle, right? One strategy to generate a cycle is to kind of generate it, I don't know, clockwise or counterclockwise, sorry, and then count, and then once you are at the end, you just connect. Another strategy would be to say, let me add all the nodes, and then for the last, and then let me create all the edges. That's a very different way of generating the graph. And the goal of finding a good order, is that you have to remember as little of the past as possible, right? You don't want something where you have to keep a lot of memory of what has already happened. I'll give you a concrete example about that. Okay? So now, how do we train? How do we train? The way we train is we use what is called binary cross entropy loss. But this is essentially a classification loss, a binary classification loss. And you guys have seen this loss already. You have seen it when we talked about how to define a likelihood of the graph where you have edges and non-edges. And here is the same, right? If there is an edge, this means y star is 1, then I'm saying what's the log probability that I assigned to that edge. And if there is no edge, then y star is 0, so this thing will cancel out. And all that will remain is 1 times log 1 minus y. So this is now the log probability of not having an edge, right? So this is exactly the same objective function that we talked about in the community detection lecture, where I talked to you about how do you define a likelihood of the graph, right? So basically the point here is this is just a mathematically convenient way to say if I have a binary thing, it's a 0, 1, and then depending on what the truth is, whether the truth is 0 or 1, only one of these two terms will survive, and I'm basically taking the probability of the edge or 1 minus probability of the edge, depending whether I don't want the edge to be there or I want the edge to be there, okay, based on my training data, right? So in some sense, right, if we saw the edge, then we want to make this y, this probability y larger. So we want to make minus log y larger, and if there is no edge, we want to make 1 minus y larger, which means we want to make minus log of 1 minus y smaller. Okay, and this way we are basically fitting the data, the outputs to the ground truth samples or to the training data. Remember that this output y, this edge probability, is computed by RNN. So it means what we really do is we adjust those RNN parameter matrices. I think that if you remember, there were 3, Q, W, and V, I think I called them. Right? So really, we want to tweak those things to give us the right y values that are in some sense as close to the y star values as possible. Right? So that's essentially the idea. Because if I generate exactly the same sequence, then whenever there is an edge, I will have a probability of 1 of having an edge. And wherever there is a no edge, so 1 minus 0 survives, I will have again 1 minus 0, I will have 1. Right? So in this case, I will be able to minimize this expression. Okay? That's the idea. So let me now show you how do you put all this together and how would this work, and I'll kind of show you what is the structure of the neural network over which back propagation happens, right? So we wanna, let's assume that node 1 is already part of the graph, and now we are adding node 2. And this is the graph we will be generating, so you'll be able to follow. So the ways this will work, right, is we say now, node 1 is already there, so we now start generating node 2. So we added node 2, and now we need to decide how to connect node 2. So we first initialize the edge level RNN with the hidden state from the node level RNN, and then here we input the start of sequence. This will generate me the probability of the edge. I flip the coin with that probability. The coin said yes, so I create an edge between node 2 and node 1. I do one more step of RNN. Now I know now I can stop, and I will use this as a hidden state to the next thing, right? And when I will be training, I will be using ground truth information here denoted in red as input to the next step, right? So rather than saying here I'll flip a coin, I will just take the real edge and put it there, and I say, here I got some output, but I really wanted to generate end of sequence. Now I will take this thing, put it here. Now we are adding we have added edges for node number 2, so now we will add edges for node number 3, right? So here we generated node number 3. We take the edge level RNN, initialize it with the hidden state from the node level RNN, kick it with a start of sequence, and now this will generate us a sequence of probabilities. But rather than flipping coins and putting the state up there, we will be actually using real edges. So again, those things are written in red, right? And then, right now, if now that we have done that, now if we are done, we take the hidden state, put it in here, and here we want the edge level RNN to say end of sequence, we are done. Okay? And this is now the process to generate this graph on 3 nodes and 2 edges. Yes?
So is the intuition of teacher forcing so that at any given state you basically give it the best chance possible?
Exactly.
So you're giving it the ground truth.
Exactly. So the idea of teacher forcing is that essentially the teacher supervises you at every step. So the teacher doesn't let you wander off too far, but after every step, the teacher says, oh, this should be a 0. Oh, this should be a 1. Right? So the teacher immediately corrects.
So is there a sense of, like, first of all, how much worse the training would be without teacher forcing? And second of all, maybe you would feel like you want less and less supervision as training goes on. So could you reduce teacher forcing over time?
Great question. So would you want to reduce teacher forcing over time? It will depend a bit what exactly are you trying to do, right? Because the less you are kind of forcing, the more you let the model to explore. And if you are caring, for example, to do structure generation, or if you want to say first be very rigid and then explore more, you could force it less towards the end. But kind of the most effective way to train models is to use as much of the supervised information as possible. Okay? So that's the idea. But what I wanted to show you here is the structure of the neural network now over which we train. Right? When we do back propagation, here is how back propagation happens. Right? With this red thing. Right? And this is the top of the network in some sense. Right? So you see that now for every different graph, we will have a different sequence at the bottom, a different sequence at the top, and this is how the back propagation works, right? How these inputs are proper and these outputs of the model, how these differences, in some sense, are propagated through for the parameters to be updated. Yes.
Each edge level RNN seems to have one more stage than there are edges, what is the purpose of the last output?
The purpose of the last output is to say end of sequence and to take that thing and feed it to the next node level. So I'm doing one more update of the state so that the node level thing gets the updated state. That's the intuition. The same question? All right, good. So this is how this will work. So how are we now generating the graph? Essentially, we do the same thing. The only difference is that now we take these probabilities for real, we sample them, and then we put them in, right? I generate a probability, I sample it, and now I put it in here to generate a new probability, sample it, put it up there, I get the new thing, and then push it down. Okay? So that's the idea. So quick summary, what did we learn? We learned to generate the graph using this sequence of sequences type of model, where we use the recurrent neural networks to generate the sequence. And essentially you can think of this is that we are printing out this matrix in this way. And the key step here is, right, that we have this notion of a hidden state, and the hidden state is kind of the representation of everything we have generated so far, so that we know what the next step should be. Yes?
How do we sample the end of sequence token? Because if you can go to the previous slide.
Yes, I know.
Yeah, so because this is the probability of having an edge or not an edge.
Yes, so there are, you can think of it differently, right? It will depend on exact implementation details. You can just think of this end of sequence as a true final state, and you could push this in. The question is, in some sense, how many dimensional the token is, and what exactly are you pushing it here? And this will depend a bit on the exact implementation details, the way you want to do it for your application. Yes?
Since we know how many edges we want to predict,
yes,
why is there a need to predict end of sequence? We can automatically feed end of sequence in the next.
Exactly. You can do that. The reason, this was the question before, the reason why we decided to do it this way is that you get yourself to update the hidden state again. So it gives you more flexibility to update the hidden state. Yes?
So is the size of your node sequence fixed?
No. Size of node sequence is not fixed because I continue doing this until this guy will output end of sequence.
So I guess inside of this node RNN box here, what is how many, like how, for example, how do you decide how many RNN cells you want to use?
You use until you generate end of sequence. So until the thing will say I'm stopping, right? So at the training time, this is all this is fixed, right? But at the test time, you will run until the network will decide I don't wanna do that, right? How would you, for example, decide? You can decide that here you are generating an end of sequence, or another way you can think of it, if the output here and the input here gives you the end of sequence type event, you will stop, right? So that's how you do. You need to know how to explicitly stop at the node level. Okay, last one.
Yeah, you might cover this if it's the next thing just coming out. But so in practice, RNNs have a vanishing gradient if the sequence gets very long, and it seems like compared to text or other things that your graphs are going to get really huge. And so what are the sort of strategies that you use to stop the gradient from vanishing as you're generating your edges?
Great, next slide. All right, it's really next slide. All right, good. So what's the problem? The problem is exactly what you said, right? When I generate the last node, here I need to remember, does it link to node number 1? Does it link to node number 2? So if I want to generate a graph on 1,000 nodes, when I add the 1,000th node, I need to remember everything I have generated so far, so that I know whether the 1,000th node should link to the first one or not, right? And that seems very kind of intractable. So, right, exactly the same point, right? Any node can connect to any prior node. So, and this means there will be kind of too many steps to keep in mind or too much to memorize to generate the graph, right? In principle, we need to generate the full adjacency matrix. These are too long dependencies. I need to memorize too much, right? Because essentially, I take the graph, and here is what I'm generating, right? I'm generating this type of recipe to draw the graph, right? And the issue is that in principle, right, if I would use this type of node ordering, I would now say generate node 1, generate node 2, don't generate an edge. Then I would say generate node 3, generate 2 edges. Generate node 4, generate 2 edges. And then generate node 5. Now I need to remember that I need to link all the way back to node number 1 and node number 4. Right? So the difference between node IDs is the amount of memory I need. Right? So the question is, how do I limit this complexity? And the answer is, in some sense, amazingly simple, but also very profound. And the answer is that I can do what is called the breadth first search ordering of the nodes. Right? I start at some node, and I take its immediate neighbors. And then I take neighbors of neighbors. And this means that the IDs between the nodes that are connected will be as small as possible. Right? So if I renumber the nodes this way, then I have to remember much less. All I have to remember now is 2 steps of memory, right? I just need to know to be able to connect 2 steps back, right? Rather than be able to need to connect, 4 steps into the past, right? As we had before with this type of ordering, where here I had to remember to connect to node 1. Here, all I have to remember is to connect from 4 to 2. Right, that's kind of the farthest, or from 5 to 3. That's the farthest into the past I need to remember. Yes?
So the maximum memory required relates to the degree of the nodes.
It will relate to the degree of the node. Yes, it will relate to the degree of the node. Yes?
Would this still be bad on like I'm thinking like a huge social network graph is a small diameter, right?
Yeah.
So then like your BFS is still gonna stack up like the order of
That's a great question. So of course this will depend a bit on the structure of the network, but this model is the best thing there is out right now, and it can give you graphs of around 1,000 nodes. Other deep models are able to generate graphs of around 10 to 20 nodes, right? Because this is hard. And essentially, let me just say what do we do and why does this give us opportunity? First is because we are using the node ordering. Now, as I said, we don't need to learn that 5 links to 1. And this means we need much less kind of memory. So the model capacity is smaller. We reduce the number of possible node orderings. We just pick one rather than say, let's take something random. And we also reduce the number of steps in the edge generation. And why is this the case? This is the case because before we were generating the entire adjacency matrix. Now, all we need to generate is this band, right? Because you know how far into the past a node goes, right? So a given node only generates to an edge the previous one, the previous one, and the previous one, right? So you don't need to care about this, right? And real networks are amazingly sparse, so you can make them kind of dance on the diagonal and essentially be nothing of the diagonals, right? That's essentially clustering of the networks. And again, if you go to the earlier lectures, I actually showed you the structure of these things. And if you order nodes and edges correctly, you will have this kind of block diagonal structure, right? So why is this now elegant? Is because when I learn to generate, I don't need to generate all this area. All I need to generate is this band here, right? This is what our node ordering gave us. Yeah? Yeah. Okay, the best. Good. So let me now show you some examples. The way you can test this, right, is this notion. I have a training set of graphs. I have the test set of graphs. How do I compare? The general strategy is that you compute some properties of the nodes here, and you compute some property of the graphs here, and you compare those properties, like the clustering coefficient, diameter, degree distribution, things like that. You can match the metrics or the properties of the graph. So that is usually the strategy. What I will show you is only examples, where these are the training ones, and this is now what the model generates. And here I show you 3 models. You already know what the Kronecker graph model is. You don't know what this one is yet, but it's some kind of stochastic model, and we will talk about Barabasi Albert later. But this is kind of a statistical machine learning model. This is a kind of a very mechanistic graph generation model. Like, think almost like the small world model. And you see that none of them can generate a grid, right? We are able to generate the grid because the process is stochastic, right? Like, like here, notice we make a mistake. Here is one mistake, but we generate the grid, right? And if you think about how to generate the grid, you basically need to learn. Like, it's almost like when you are knitting. You need to know when to stop and start again or whatever, right? So we are kind of generating the graph. And again, we know when to stop, right? So these grids have different sizes, okay? So these are the grids. These are what is called ego networks. Again, pictures on the top, what comes out of the model. And these are these other 3 models. And again, like, just visually, right? This kind of seems okay. This maybe seems a bit better. This is totally off, right? So kind of the point is that all these models contain certain kinds of inductive bias, so certain kinds of priors that make them useful to generate very specific networks, right? They are not meant to generate grids, so they cannot generate grids. Our model can learn to generate the grid. These, right, they are kind of meant to generate this kind of networks with high degree nodes and low degree nodes, but this guy fails here as well, because this model is meant to generate graphs with community structure, right? So here, the model actually generated something that looks quite similar to the training data, but then the other 2 models fail miserably, while the graph RNN works quite well. All right? So just visually, you can see. So I have 5 minutes left. So let me now show you an application and talk about some open questions, and then I'll be done. So at the beginning, I was making this case. Could you use this to generate graphs? Generate molecules, right? Molecules are cool because you want to generate molecules that are chemically valid, right? Chemistry has rules, that they are realistic, and that optimize certain chemical properties, right? So the idea is that you have a model. The model outputs a real molecule that optimizes some property. For example, drug likeness is one of the properties chemists care about, or solubility, or toxicity, and so on. Okay? And I will just show you how you do this, right? You say, I want to optimize a given objective, so you assume you have some black box that tells you how good value of that objective did you achieve. You want them to be valid, right? So that obeys underlying chemistry rules, so that, you know, oxygen doesn't have 26 bonds. So you need to know the valency of different atoms. And then you want this to be learned from examples. And it is important because you want your molecules to be realistic. And why is this especially important is that especially if the molecule, it's very easy to find kind of a Frankenstein molecule that obeys rules, but it's totally unrealistic and maximizes some objective function. But when a chemist looks at it, says, I'm never able to synthesize this will break apart immediately, this is unstable, this is unrealistic. So you want them to look like real molecules so that you can potentially synthesize them. You want them to obey the chemistry rules and to maximize this black box. And I'll just show you some examples and tell you how to do this. We will actually, in this case, we will combine everything we have learned so far. We will use graph neural networks to capture the state of what we have generated so far. So this is what we'll use here. And the other pieces I won't explain, but I'll just mention them for people who know what I'm talking about. So we will use reinforcement learning, which allows you to do delayed reward type computations to get the final reward. When we generated the molecule, only then we can ask what are the properties of it. So this will be the final reward. Our intermediate rewards as we generate will be whether we generated a chemically valid step. Right? Whenever we obey the valency, we will get some little reward. And then we will now use this technique from machine learning called adversarial training that will allow us to say whether a given molecule looks realistic or not. Okay, so these are kind of the three technologies we will combine. How do we capture the state using graph neural networks, reinforcement learning to get the final reward based on the objective value of the objective we want to maximize, and then adversarial training that will tell us whether we imitate real molecules well enough. I will only say this much. There is a paper for those who are interested. What I want to show you now is some pictures. I'll show you two pictures. Here we are optimizing some property that chemists call log P. And here are the molecules we generate and the values of this log P property. These are realistic molecules. This one is unrealistic, but you see how well we can do, right? But if you have you ever seen a molecule like this? Probably not, right? And then this is another objective function called QED. This is quantum energy. And again, these are kind of the molecules we generate. And here are the values of the objective function. What is super cool is that you can also do molecule completion, right? We can take a partially built graph, and then we can initialize the neural network to take it from there on. So you can take a partially completed graph. Here is its log P value. And then we can run the method to complete the graph. And here is the log P value now. And you see how it goes from -8 to -0.7, or from -5.5 to -1.8. So you see how basically we can complete this, keep the original structure, but improve the value of the property a lot. So what are some interesting problems? Interesting problems is how would you use this to generate graphs in other domains? Maybe graphs of 3D shapes, right? You can represent 3D shape as a graph, point clouds, scene graphs, things like that. How do you scale this to larger graphs? As I said, the technology I showed gives you to go to about 1,000 nodes, but that's tiny from a certain point of view. For molecules, it's big because molecules are usually small. I know, a few tens of nodes. There is interesting ideas would be, right, do you need to generate this really as a sequence of nodes and edges? Could you do some kind of hierarchical generation? Could you generate entire subgraphs, like little building blocks? In molecules, in chemistry, you have these building blocks like benzene rings, and you just say, drop the benzene ring. As I said, kind of adding higher level structures. And then there is a lot of interesting applications to anomaly detection and kind of everything I've said up there. So with this, I'm done. Thank you very much, and thank you for all the questions. It was great. Thank you.